Hello everyone, and welcome to the Bias-Variance Trade-off lecture. In this lecture, we're going to discuss the bias-variance trade-off and how you can use it to evaluate your model's performance. Bias-variance trade-off is a fundamental topic of understanding model performance and evaluation. Go ahead and review Chapter 2 of an Introduction to Statistical Learning for a more in-depth look on this topic. The bias-variance trade-off is the point where we are just adding noise by adding model complexity or flexibility. The training error goes down as it has to, but the test error will start to go up. The model, after the bias trade-off, begins to overfit. Let's go ahead and discuss this topic by imagining a dartboard. So imagine that the center of this target, or dartboard, is a model that perfectly predicts the correct values. As we move away from the bullseye, our predictions will get worse and worse. And we're going to go ahead and make a quadrant of low variance versus high variance and high bias versus low bias, so we can get an understanding of what the bias and variance terms mean generally. Imagine we can repeat our entire model building process to get a number of separate hits on the target. Each hit represents an individual realization of our model, given the chance variability in the training data we gather. Sometimes we will get a good distribution of training data, so we predict very well and we are close to the bullseye, while sometimes our training data might be full of outliers or non-standard values, resulting in poorer predictions. And these different realizations result in a scatter of hits on the target. What we're aiming for is something with a low bias and low variance, but realistically what you'll have to do is trade off variance for bias. And here we can see in the quadrant of the target, a low variance, low bias model will predict correct values on the bullseye. A low bias, high variance model will predict values around the bullseye but with a high degree of variance, versus a high bias, low variance model in that lower quadrant will have a high bias to a certain location but low variance, so all your model's predictions are in a certain area. And then the worst, high variance, high bias, means you're just all over the place, basically. A common temptation for beginners is to continually add complexity to a model until it fits the training set very well. And let's go ahead and begin to understand this in a machine learning algorithm we already learned about, linear regression. What you may want to do is, let's say you're given a set of red training data, not your testing data, just your training data. You might have a simple model, such as a blue line, and you get a certain error on your training data. And you decide as a beginner, hey, maybe I should just make the model more and more complex or flexible so that it hits all those training points. However, if you're hitting all those training points, your model is going to fail to predict for new test points, which is why we do that train test split. Doing that can cause a model to overfit to your training data, and like I mentioned, cause large errors on new data, such as the test set. What we're going to do is take a look at an example model on how we can see overfitting occur from an error standpoint using test data. We'll use a black curve with some noise points off of it to represent the true shape the data follows. Alright, we have three images here. The first one is the X versus the Y. And here we have model flexibility as different linear fits, a linear fit, a quadratic fit, or a spline fit, with each one getting more complex. So the simplest is just a linear fit. More complicated than that is quadratic, and then you can have a spline fit. And you'll notice that the black curve is the truth that the model actually follows. So all the points are just noise around the actual black curve, which is the truth. In order to evaluate your models and compare the complexities to each other, what you'll have to do is plot out the complexity or flexibility of the model, for instance, the polynomial level of a regression fit, versus the error metric, such as mean squared error. And you can see here in that middle plot, that's exactly what we've done. And we've plotted it out for the training data versus the test data. You'll notice all the way to the left, we have a simple model, that yellow linear model. For this model, we have a high error on both the test data and the training data. As we begin to get more complicated with the quadratic model in blue, we begin to lower the error for the test data and the training data. As we get even more complex, however, we begin to lower the error for the training data significantly, but as a result, you begin to raise the error on the test data, the new data. So you want to find a point that's going to balance out the bias and the variance. In this particular case, that's going to be closer to the quadratic fit, that blue point. So you want to balance out the bias and variance of your model to the point where your test data and training data have reached some sort of minimum and grouping together. This is a classic plot to show this as a general stance where you have low versus high model complexity on the x-axis and some sort of prediction error on the y-axis. And as you move to the left, you get a higher bias but lower variance. And as you move to the right to a higher complexity model, you get a lower bias but high variance. And what you want to do is pick a point where you're comfortable with the bias trade-off. If you go to the left of it, you'll start to underfit to the data, and if you go to the right of it, you'll start to overfit to the data, meaning you're hitting all those points in your training data, and new data is getting a larger error because of that. Alright, keep that in mind as we continue on using Python for machine learning. This is more of just a theoretical background. Go ahead and read Chapter 2 of the Introduction to Statistical Learning if you want a more in-depth look of this. This is a topic you want to keep in mind as you begin to work with real-world data. Okay, thanks everyone, and I'll see you at the next lecture.